Hi, this is Shinyoung from KAIST. Our work is entitled Differentiable Transient Rendering. Rendering simulates light transport as a 2D image. This rendered image can be considered as a function of scene parameters, which can indicate any numeric values describing the scene. Differentiable rendering allows us to compute derivative images of the image with respect to scene parameters. In recent years, many works have investigated how to compute derivative images. However, all these works assume steady-state light transport where the speed of light is infinite. To simulate light transport phenomena with the finite speed of light, we need transient rendering techniques. In transient rendering, the light source emission and the source sensor sensitivity of a scene not only depend on positions but also on time. Moreover, the speed of light is finite. There are also several works which serve inverse transient light transport. However, these works have several limitations, such as the limited numbers of light bounces up to 3. In this context, by combining differentiable rendering and transient rendering together, we propose the first general-purpose differentiable transient rendering method that allows us to compute derivatives of transient images. In steady-state rendering, the radiometric measurement of a sensor pixel can be computed by the path integral formula. An important property of steady-state path integral is that each term in the integral only depends on 2 or 3 consecutive vertices, so that the path integral can be considered as recursive 2D surface integrals. Using this property, Zhang derived the differential steady-state path integral formula by applying the Reynolds transport theorem to those 2D surface integrals recursively. In transient rendering, the radiometric measurement can be computed by the transient path integral. The transient path integral contains the time of flight term, which depends on the all vertices of the light path. Due to this term, it is hard to reduce the transient path integral into separated lower dimensional integrals. So to differentiate the transient path integral, we need to directly handle the high dimensional integral over the path space. Since the Reynolds transport theorem can only treat 2D surface manifold lying on 3D space, we use the generalized transport theorem. Additionally, we reduced the time integral in the transient path integral by defining the correlated importance function as the cross correlation of the source and the sensor functions in the time dimension. In our differential transient path integral, using steady-state terms obtained by the existing methods and our correlated importance function, we can compute the interior term and the boundary term. Now we will introduce the inverse rendering application results. First, we are estimating a rotation angle and a refractive index of transparent objects. After optimization steps, we observe that the parameters have converged as shown in steady-state images, string images in xt coordinates, and residual values. Next, while all existing non-line of sight imaging methods assumes planar geometry of the visible world, we introduce a non-line of sight tracking scenario with a wavy visible world. Then we observe that the optimized result is close to the target one as shown in string images and residual values. Finally, we tried to track a hidden object around by not one corner but 2 corners, which has never demonstrated. We can see the optimized result is close to the target as shown in string images and residual values. In conclusion, we derived the differential transient path integral using the generalized transport theorem and implemented Monte Carlo differentiable transient rendering using the correlated importance function. And we proposed several challenging inverse rendering scenarios which need to differentiable transient rendering. Thank you for listening.